Welcome to Algebra 2. This is section 4.1, graphing polynomial functions. All right, for our introduction, we got a little calculator exercise for you. So what I want you to do is pause this video and take a couple minutes to actually go through this process. Make a sketch of each of the functions, and see what you what kind of patterns you can discern from those different graphs, and then let's make a prediction about what we'd expect the last function to look like, the one that's provided in number 3. So pause the video, take a couple minutes and try that. I will check back with you in a few seconds. Okay, so hopefully we've got some graphs in mind sketched out here. So for 3x plus 1, we have a steep sloping line up to the right with a y-intercept of 1. For letter B, we should know that this graph is a downward-facing parabola that is twice as tall as you would expect it to be. And it's also, it appears, shifted off to the right just a bit. So here, let's see, probably something like that. And again, we're just making a quick sketch. All right, letter C, we've got a cubic function. This is a new one. So we probably see something like that, and it's probably a little bit more pronounced on your graphing calculator, probably something a little bit more steep like that, but you get the idea. Letter D, here we probably see something like that. And in letter E, we probably see, let's see, something like this. Something like that probably, but again, yours would probably be much more steep than that, just to kind of emphasize what those graphs look like. So what do we notice each time? Well, we go from a function that has x to a function that has x squared, then x cubed, then x to the 4th, then x to the 5th. So what do you notice about the graphs? As the powers increase, the graph bends more. We may notice that with odd powers, like x to the 1st, x to the 3rd, x to the 5th, odd powers mean the graph goes in different directions. Whereas if we had even powers as our highest powers, the graph takes the same direction. And you may have noticed some other things about those graphs. What do they have in common? But we're looking for patterns here. We're trying to make a prediction here. So what would we expect this final function to look like? 1/3 x to the 8th power, then a 3x to the 5th, and a 2x squared plus x. We would expect both ends to go up. We would expect it to be 1/3 as tall as an x to the 8th, 1x to the 8th function. And we would expect to see at most 7 bends. Right, because if you look at, if we have x to the 1st, there are 0 bends. X to the 2nd, there's 1 bend. X to the 3rd, there are 2 bends. It seems like the number of bends is 1 less than the highest exponent we see. All right, and if we were going to do this, I have another video on my YouTube channel called Sprinters, Intermediates, and Distance Runners. It's an honors pre-calculus lesson, but that kind of teaches you how to get the general shape of a function. So there's no constant, which means we're at a 0 y-intercept. Next, I see a plus x, which means I'm sloping at a positive 1 slope for an instant. Then I see negative 2x squared, which means as I move away, I start to look like a downward-facing parabola. Then I see 3x to the 5th, so I know the right-hand side must rise Left-hand side must continue to fall like a fifth degree. They go in opposite directions. And then finally, I see 1/3 x to the 8th. Well, it's positive 1/3 x to the 8th, which means the right side continues to rise, and the left side has to turn and rise eventually as well. So we probably see something like that. It didn't have all 7 bends like we would expect, but it definitely is bending more than a line, and the ends are going in the same direction. All right, so now to the actual textbook work here. A polynomial is a function, and this looks gargantuan, but really look at the pattern that's happening here. We need to understand the math language a little bit. So we've got our function is some coefficient times x to some power, and then we can keep adding powers that decrease and decrease until we get to something that's just a constant, just a number at the end. So a sub n cannot equal 0. So that means that if we have an nth degree polynomial, that we are seeing something to that power. So we've kind of been building our library of functions as we've gone, and constant functions are considered a polynomial. That's just f of x equals a sub 0. We have seen linear functions. That's where our highest value of n is 1. So we have x to the first power. We keep building that. We go on to quadratic functions. Then we have second powers emerging. So where we're going with this is we're setting up polynomials that have greater powers than 2. All right, so here we have kind of our library. As we build these up, we've got some names for each type of function. So we've got a constant, we've got a linear, quadratic. We're going to add a cubic function and a quartic function. And we classify these polynomials based on their degree. And the degree, you can see 0, 1, 2, 3, 4, that just indicates the highest power on x that we see. So we've got x to the first, x to the second, x to the third, x to the fourth. And these are just common ones to know the names to. We can have 8th degree polynomials like we saw in our introduction. This pattern definitely does continue on. All right, another thing we hopefully picked up on the introduction is that depending on how the degree looks, we can see different behaviors of the ends of the graph. So our first 2 boxes here cover when the degree is odd. We said in our introduction if the power was odd, that the graph moved in opposite directions, and that's true. So if we have an odd function with a positive leading coefficient, that's like y equals positive x. Again, that's like to the first power. Think about that line. It rises to the right and falls to the left. Okay, and that same rising and falling would happen if that were positive x to the 7th power, any odd power. Now notice how the book is describing this. This is very, very important language to understand if you want to really have a leg up on your calculus classmates later on. What this is saying is the height, f of x, is approaching positive infinity as x, the left and right, approaches positive infinity. So as I go to the right, the height is increasing. And likewise over here, the height is decreasing as I move to the left. F of x means height, x means left and right. Now if we have an odd degree with a negative leading coefficient, that's like y equals negative x. Or we could think of that as negative x to the first. It's a vertical flip applied, or our function is simply a negatively sloping line, so to speak, the most basic one. Okay, but again, look at the language. Our height is increasing as our x is going to the left. Our height is decreasing as x approaches positive infinity, as x moves to the right. In the lower half down here, if our degree is even and our lead coefficient is positive, we'll think about what y equals positive x squared looks like. That's a basic positive even function. The ends are going to tend in the same direction. So here if we have a positive function with an even degree, my height increases as my x goes to the left. My height increases as my x goes to the right. All right, and likewise, an even degree with a negative leading coefficient, that's like y equals negative x squared. The vertical flip is applied. Now my height is decreasing as x goes to the left, and my height is decreasing as x goes to the right. All right, so just some things to keep in mind. These are all patterns that help us understand how the graph behaves. Our first example, decide whether or not the function is a polynomial function. If so, write it in standard form. Okay, that means exponents decrease as we move from left to right. And then state its degree and leading coefficient. And if it's possible, we should classify that using the table that we covered earlier. All right, well, p of x, if we put that in standard form, the highest exponent I see on a variable is x to the fourth. So that's my leading term, 6x to the fourth. Then I've got a minus 4x cubed. Then I've got a plus, a positive, 1/2 x squared. And then a plus 3x and a minus 1. All right, it is a polynomial because we notice that all of these x terms can be expressed as a positive exponent, or a zero exponent, as in this last one is like negative 1x to the 0th if we wanted to keep that pattern going. So all of our terms can be expressed as x with a 0 or greater exponent. That is counting up in integers. So yes, it's a polynomial. And its degree is 4. That's the highest exponent we found. That means it's a quartic function. And the leading coefficient is the coefficient on that fourth power term. It's a 6. So we would expect a graph of this function to rise to the left, or as x approaches negative infinity, that's saying going to the left, my function's height is approaching positive infinity. And we would expect it to also rise to the right. So as x approaches positive infinity, the height is also approaching positive infinity. Now, they don't ask us for that, but we should know that about the graph and know how to express that mathematically. All right, number 8. As I start to look at this and look at the powers, I see this weird term, negative 5 over x. Well, this is a reciprocal term, and we cannot have that if it's going to be a polynomial function. We want x to some power that is 0 or greater. So here, this is not doing it. So not a polynomial. All right, example 2, evaluate the function for the given value of x. Well, evaluate means to plug in. So we just want to find h of negative 1/3. That means I'm doing 5 times negative 1/3 to the third power, minus 3 times negative 1/3 to the second power, plus 2 times negative 1/3 plus 4. Now, just like with squaring, when we take a fraction to a power, we are raising both the numerator and denominator to that power. So this is equal to 5 times, if it's a negative number to the third power, that's a negative times a negative times another negative. The negative stays on. Negative 1 cubed over 3 cubed, that's 3 times 3 times 3. It's very tempting to call that 9, so be careful. Minus 3 times, here I've got a negative number and I'm squaring it, so I know that will end up being positive, 1 squared over 3 squared. Plus 2 times negative 1/3, well, if I have 2 negative thirds, I have negative 2/3. And then plus 4. So I got negative 5/27 minus 3/9 minus 2/3 plus 4. Let's get a common denominator so we can add all those up. If we're plugging a number into a polynomial, we should get a number out. So negative 5 27ths minus, let's multiply top and bottom by 3, 9 27ths. Multiply top and bottom by 9 minus 18 27ths. Plus, multiply top and bottom by 27, 108 27ths. Okay, 5 and 9 and 18, that's 32 that I'm taking away. 108 minus 32 is 76 27ths. Okay, and that is our final answer. Now we could use a calculator and do the math to fraction key if you wanted. Just be careful, if you were doing this in a calculator, first of all, make sure a calculator is allowed. But make sure that you would type in negative 5 divided by 27, put that in parentheses so the calculator knows how to do the division, then minus 3 divided by 9, minus 2 divided by 3, plus 4. And then it's the math key. And the first option is arrow FRAC. That will turn your answer into a fraction. So you would hit enter after typing in all that, get a decimal answer, then hit math to fraction, and it would hopefully tell you 76 27ths. Always a nice way to check tricky fraction work as well. Example 3, describe the end behavior. Now, if you have looked at other YouTube videos or maybe in other classes you've taken, you've heard that, oh, the teacher will accept it, that you say it rises to the left and falls to the right. But we want to, again, this is Algebra 2, right? We want to step up our game a little bit, get ready for future math classes and other math courses we may have to deal with. So we want to use that mathematical language. So here I notice I've got a positive leading coefficient and an odd power. So positive and odd. That means that my graph is going to rise to the right and fall to the left. It's going to act like positive x to the first. Okay, our basic odd function. So how do we write that? Well, as my x goes to the left, that's towards negative infinity, the function is falling. So the height is approaching negative infinity. And as x approaches positive infinity, that's to say it moves to the right, then the height is increasing, approaching positive infinity. All right, for number 20, here you want to be careful because it's easy to look at this and say, well, there's no x term here. What's that function doing? Maybe it's a constant function. It is not in standard form. Now, we don't have to go through all the work to write this out in standard form like we did in earlier examples. We just need to be able to pick out what that leading term would be. In this case, that term with the highest exponent is this negative 5x to the 5th. My leading coefficient here is a negative 5, and that power that is on that term is a fifth power, an odd power. So it is falling to the right and rising to the left. Okay, let's put that into math speech. As x is going to the left, then that function is rising. And as x is going to the right, that function is falling. But again, we want to use those arrows to indicate the x approaching positive infinity, moving to the right. Same thing with our f of x's, our heights. All right, example 4, graph the polynomial function. Well, unfortunately, we just got through all this work in chapters 2 and 3 dealing with quadratics, and we had some really nice tricks with axis of symmetry and, made our table of values very easy to calculate. It's not necessarily the case here. We can always fall back on a table of values, and I definitely encourage you to do just that. But we want to pick some values that we are sure will stay on our screen. So here, since we're going to the third power, it might not be a bad idea to keep our numbers between -2 and +2. So let's see what happens when we compute our y values. So negative 2 cubed is negative 8. That negative sign stays. Then plus another negative 2 and plus 3, I get negative 7. All right, for negative 1 as an input, I get negative 1 minus another 1, and then plus 3, that's a plus 1. At 0, I have 0 plus 0 plus 3. At 1, I've got 1 plus 1 plus 3. That's 5. And at 2, I've got 8 plus 2 plus 3, 13. So, oops, plotted that point in the wrong spot. So I'm off my page up here. You can see that graph, it is bending, but not as sharply as some of the ones we saw in our introduction. Try and connect these on the tablet here. It's kind of tricky. I apologize. There's our graph. Now, if we were to look at this graph and try and analyze it, the domain would be all real numbers. There's no x value that I cannot plug into that function. The range as well, negative infinity to infinity, because all the way from bottom to top, I'm going to see that graph. It extends infinitely in both directions. Same with the domain. It doesn't look as obvious, but this graph will continue to creep off to the left and off to the right. If I plugged in negative 50, I would get an answer. If I plugged in positive 100, I would get an answer. All right, here's another polynomial function to graph. We're still going to use just a table of values. I'm going to put it into standard form just so it's easiest to work with. And now 2 to the 4th power is 16. So I want to think pretty carefully about what values I choose. Again, negative 2 to positive 2 are pretty good ones to choose. If the points are off the screen, we just won't plot those. So if I plug in a negative 2, I get negative 2 to the 4th, which is 16, but that's negative 16 because of that negative sign out in front, plus 3 times negative 2 squared, that's 12, plus 5. At negative 2, my graph is at a positive 1. Negative 1, here we've got negative 1 to the 4th, which is 1. But again, we got that negative sign out front. Plus 3 times negative 1 squared, plus 5. So here we're up at 7. Oh. Keep plotting points wrong. I apologize. The axes are kind of difficult to see on this graph. If I plug in a 0, that one's easy. Positive 5. If I plug in a 1, I have 1 plus 3 plus 5. That's 9. Oops, sorry. Negative 1 plus 3 plus 5. That is a 7 again. Can't forget that negative sign out front. We don't have that same symmetry that we had with parabolas, unfortunately. And at 2, here I've got negative 2 to the 4th, plus 3 times 4, plus 5. We do get a positive 1 again. So I guess there is some symmetry with this graph. We kind of lucked out in that regard. We get kind of like a capital M looking thing, a couple of bends in it. But let's take a look at domain and range. So the domain of this function, again, I could plug any x value and nothing would cause it to break. It's not limited. My inputs are not limited. The range, I see that function will continue to go downward to negative infinity. I'll always have a height output, but I don't see any heights that are higher than 7. So from negative infinity up to 7, those are the outputs that come out of that function. Those are all the available heights. Example 5, I think this is quite possibly one of the most, what's the word I'm looking for? If you can understand this type of problem, then I know you get it. It's very indicative of who understands the work and who doesn't. So it's very beneficial to practice this type of work. The function f is increasing when my x values are between -2 and 3. That means that the graph is rising there. It's gaining height. And it is decreasing when my x value is less than -2 and it's greater than 3. So I know it's going down for a while, then it hits -2, it increases for a while, then it hits +3, and then it starts decreasing again. All right, the function is positive, greater than 0. That means it's up above the x-axis. The height is greater than 0 when x is less than -4. And also when 1 is less than x, which is also less than 5. And our function is less than 0 when x is between -4 and 1, and when x is greater than 5. All right, so let's see what we can sketch out here. We're kind of like police artists. Well, I know that my graph is crossing the x-axis at -4, 1, and 5. Those are the places where my graph is changing from being above the x-axis to below it, where my height is going from positive to negative, or vice versa. So I'm going to sketch out at -4, I know there's a crossing there. At +1, and at 5. All right, f is increasing when I'm between -2 and +3. And it's decreasing on either side of that. All right, so let's see what we can come up with here. So our function has to come down, decrease for a while, it's decreasing, it's decreasing, it's decreasing, then it hits that x equals -2, makes a bend and starts increasing, crosses again, it's still increasing, then it hits that x equals 3, and begins to decrease from there. Okay, and it's not really relevant what heights our function has at those values. It could be anything, but we want to be sure that we show the decreasing, increasing, decreasing, that type of bending in the graph, and that it crosses through those points that show where it's changing sign from having a positive height to a negative height. Very, very cool example. I really like this one. I would put a star next to this one. That's a winner. And example 6, here's a calculator problem. The weight of an ideal round-cut diamond can be modeled by this function, and it's a cubic function, where W is the weight of the diamond in carats, and D is the diameter of that round-cut diamond in millimeters. What is the weight of a diamond with a diameter of 12 millimeters? Okay, well, let me open up the calculator here. And let's take a look. So here we want to evaluate this function with 12 as an input. So 0.00583, it's just a calculator problem, times 12 to the third power minus 0.0125 times 12 to the second power plus 0.022 times 12 minus 0.01. So I'm just rewriting that function, but I'm inputting a diameter of 12 millimeters. All right, and if we hit enter, we find that, wow, that's a big diamond, 8.528 carats. All right, and that is a huge diamond. but it makes sense. I mean, a diameter of 12 millimeters, that is a huge diamond, worth a fortune. But yeah, just evaluating the function and practicing typing it into a calculator. That's really all this is asking us to do. Here's a look at your assignment for section 4.1.